So, thank you so much, Dr. Parvati. I'm feeling very happy and honored and blessed to introduce today's speaker, who is known to me from last so many years, Professor Sudhir R. Jain. Professor Jain need not require any kind of introduction because whoever is associated with nuclear physics or the quantum physics, everyone knows, sir. But as a matter of formality, I would like to give an introduction in a very brief way so that we can get a maximum time to listen to his talk. Professor Sudhir Jain is currently working as a scientific officer H at a nuclear physics division at BARC Mumbai. Sir is also acting as the professor Homi Bhabha National Institute, Department of Atomic Energy. He is adjunct professor at University of Mumbai, Department of Atomic Energy, Center for Excellence in Basic Sciences. Sir has guided a number of students for his PhD degree. He has a many interest research like a non-linear dynamics, quantum chaos, non-integrable dynamics, semi-classical physics, a list keeps on going. It's always the dream of every researcher to publish research articles in the journals, top-rated journals like Physics Review Letters. One could see circa maximum publications belongs to the PRL Physics Review Letter A, E, and he is having more than 200 top-rated publications in the journals with a citation index of more than 1,700. If you start listing the awards which are received by the sir, it will take around half an hour. So I'll just name the two most prestigious awards received by sir. The one is INSA Medal for the Young Scientist, and the another is Anil Kumar Bose Memorial Award for his work relating to the geometric phases and response functions. Sir started his MSc Physics at IIT Delhi. After that, he joined BARC. Then he completed his PhD in Applied Mathematics under Professor Suresh Lavande sir, who was a student of Professor Teller, everyone knows, who is the father of hydrogen bomb. And after that, sir did his postdoc for 2 years at Belgium. He has also worked as a visiting professor at the number of institutes like Institute for Physical and Science and Technology, USA, Institute of Theoretical Physics, Netherlands, and so on. So with this brief introduction, without wasting any time, may I request Professor Sudhir Jain to deliver his talk. Thank you so much.
So good afternoon, everyone, and so am I audible? Yeah. Right. So before, right? Okay. So should we start our lecture?
Yes, sir.
Yeah. All right. So there is a very good reason why there was no light for a few minutes, because the subject is a bit difficult and I was given some more time to think about it, so I can do a reasonable job. That's the point. So this has to come up. So the subject that we are talking about today is quantum physics, which is also called quantum mechanics, quantum theory, and so on. It's basically consisted of ideas which are non-Newtonian, ideas which were instilled in our thinking for centuries, starting from Christian Huygens and Isaac Newton and so on, that those ideas had to be completely changed in some sense. I mean, not of course entirely. Nothing changes entirely. New things are built on older concepts, and the whole evolution occurs like that. But there was something which is now called classical thought, and the classical thought belongs to Newtonian thinking, which we understand Newtonian thinking, where we have done problems, you have done many more problems than I have ever done for Newtonian mechanics. And then there were wave theories, where people saw that there is propagation of sound. When we walk along the Marine Drive and we listen to the sound of waves, if we are doing music, we listen to waves, and so there was an interference of waves, and particles or localized objects were supposed not to have the possibility of showing interference phenomenon. So there were two ideas which belonged to particles and waves, and they were somehow merged around 1900, and 20 years after that there were formal description built, which was later called as quantum mechanics. There was something else also which was unified around the same time, which was done in the hands of another one of the greatest thinkers of all time, Albert Einstein, where we thought that space and time are two different things. Einstein realized that space and time have to be discussed together, and this was a very difficult idea for anyone even now to handle. You know, it is saying something like this, that if you have a phenomenon which is taking place and you are watching it from a static frame and from another frame which is moving with constant speed, like you are in a car and you are watching the same thing, it is saying that the transformations in space depend on the time in each frame, and each frame has a different clock. And we are not prepared. Even now, we are not prepared to handle that there are two different clocks for two different frames. I mean, we say that, I have a clock, it's okay. I was at home resting on my sofa, and then I am taking the car and I have not changed my clock, so what's wrong with the clock? But if you have to get all the correct things which are experimentally found, if you have to be able to explain them, then you have to unify the transformations of space and time together, and it makes a continuum. So these two unifications, one is space and time, the other unification of particle and wave, constitutes a revolution in human thought. And 100 years is a very short time for people to change their thinking. So it's a very difficult act to really comprehend the consequences of these discoveries. The consequences in terms of technology are now evident, but in thinking it takes a very long time. So we have to eventually change our ways of thinking, and we will never do that unless somebody challenges. And what is a challenge? A challenge is that if I convince you with one argument given one way, and when you are completely convinced, I present another argument for the same thing which is equally convincing, and show that the first set of argument was actually not correct. And then you're in a state of unrest. That's the goal of today's talk. If I succeed, I should be able to trouble you. If at the end of the talk you are slightly irritated with me and with yourself, then I've succeeded. If you're very happy, then I'm not succeeding. And so that's the goal. Okay. So let's do it. It will take me a bit of time because there is some machinery which is minimal to this subject. It just cannot be done in terms of feelings and expressions. So in that we are not so smart as in classical music. Can we have this dark here so that Can these lights, some of the, no, these lights, can these lights, ये जो lights है ना, can we switch off these lights? Right. So we are talking about the subject of Nobel Prize in physics right now, and these are the Nobel laureates. In brackets you see are the ages. Is this also like a pointer? Yeah. So these are ages, the present ages, and so you see these are contemporary people. They were brought up together. They belong to the same times. They were in school together. They were not separated in time. So these are the people: John Clauser, Elena Spey, and Anton Zeilinger. In US, France, and Austria. So, yeah, okay. And the essential idea for which they are given Nobel Prize is the idea of entanglement. Entanglement is an idea which is very representative in terms of the English word entanglement. So it's not very complicated to get an idea like entanglement. If something is entangled, then it's not disentangled. It's entangled, you can't take it apart, you know. So, and according to Erwin Schrödinger, these are also ages of these people at that time. According to Erwin Schrödinger, this is not one of the traits of quantum mechanics, but it is the characteristic trait of quantum mechanics. If there is anything in quantum mechanics which is not there in classical physics, it is entanglement. And so this is, in this way, it is very fundamentally different. And the other person who thought about entanglement was Albert Einstein and his two younger colleagues, Boris Podolsky and Nathan Rosen, where they wrote a very influential and important paper in 1935. The title was, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" This title is mind-blowing because of many reasons. It does not belong to the scientific culture of that time. At that time, nobody was thinking about completeness of quantum physics or completeness of a physical theory. People assumed it must be complete. I mean, we have done everything correct. We are doing all the maths in physics right, all steps right, so we should be fine. But Einstein had a friend who was one of the greatest logicians in the history of human thought after Aristotle, who was Kurt Gödel. And Einstein with Gödel in his 20s had proved two incompleteness theorems, where he proved theorems which were like, if you have a complete set of axioms and you build a theory out of that, then it has to be necessarily inconsistent. The second theorem was, if you somehow make your system of thought completely consistent, then you can actually make statements which are undecidable. You cannot say if it is right or wrong, so it becomes incomplete. So inconsistency or completeness, consistency or completeness, you have to choose between them. And this as a human being, as our normal day-to-day thinking, we do not accept this. We want to be consistent. We want to be complete in our description. We don't want to choose. But I mean, here is a mathematician who proves theorems, and he says it's not possible. So this creates a lot of problem. And I'm sure Einstein was influenced by Gödel to consider this, and he wrote this paper. The other thing that is written here is the physical reality. When he said physical reality, it means in the following sense, that if you observe something and you can make measurement and have an answer, that's real. Right? If you have to just imagine that it must be like this, that's not real. So in very common words, people say that, is the moon there when you are not looking at it? No. It's not to be taken literally, but it's in that spirit that one is saying this. So that is a concept which will play a very important role in our. Now, what is entanglement? Entanglement is connected to the other idea which is called non-separability, and that idea is very simple to understand. How is entanglement created? Entanglement is created by interaction. Interaction, for example, if you consider an atom, something like a helium atom, because a hydrogen atom is too simple. There is just one nucleus and an electron. If you take slightly difficult problem, which is a helium atom, you have one atom, one nucleus, and there are 2 electrons. These 2 electrons make a cloud around the nucleus, and the nature of this cloud is something like this, which is depicted here in terms of the peaks. This and this correspond to the 2 electrons, and there is a nucleus, so there is a kind of one cloud. The interaction of electrons among themselves and with the nucleus is such that the wave function, which is this pattern written here, this is a wave function, which is the solution of a wave equation which is satisfied by the de Broglie wave. I mean, we understand that we can assign a matter wave to every massive particle object which has a momentum. So if the momentum is p, then Planck constant divided by p is the wavelength. So there is a wavelength associated with any material particle, and if there is a wavelength, if there is a wave nature, there should be a sort of delocalization. There should be a certain pattern which is a solution, which is a stationary solution. So this wave which is associated with the material particle, this wave satisfies a certain equation, and that's a Schrödinger equation, and one can find solutions. So this is how the solution looks for the helium atom, and you see it is delocalized, etc. But the other point about this is that although there are 2 electrons which make a helium atom, this wave function cannot be written at the level of mathematics as a product of a function which only depends on the coordinates of one electron times another function which only depends on the other electron. You can't write it as a product of an electron's coordinates multiplied by a function which is only dependent on the other electron's coordinates. There is just one function which involves both set of coordinates, and they are not separable. You can't write them as a product. So that's non-separability. It's very well known, the non-separability. So there are other examples where non-separability can be created by boundary conditions. So if I have a particle which is moving freely inside this shape of a box, and it's going like this, reflecting from this wall, coming back and doing like this and going around in this, and I solve this wave equation, I get a solution like this, which is also not separable in the coordinates like x and y. I can't write it as a f of x times g of y. I can never do that. That's also non-separable. This is another example, very beautiful, which is in 3 dimension. So one can make these functions, and these are not just some mathematical functions. These are things which you can actually realize in labs and so on. So now let's come back to the main talk and some concepts associated with them. Now, I assume that you know what are photons, and photons were introduced in some sense in 1900 in the hands of Max Planck, and photons have polarization states. So we have seen polarizers. Those of you who use goggles will know that they are polarized, and some of you who have modern watches, the top of that is polarized, and so there are Polaroid glasses. And when we say polarization states, we mean the following: that electric field at some fixed z, so imagine that there is a coordinate system x, y, z in the way you want, and these are the 3 coordinates. So if there is a phase factor like cos, so some amplitude which is just polarized along x, so that's like horizontally polarized photons. There's a vertically polarized photons. Then there can be right circularly and left circularly polarized photons, which can be written in terms of these states. You can combine them, and then realize these polarization states. So these are the polarization states. They are all orthogonal, and they are normalized to 1. So they are orthonormal states. All of them are orthonormal. So these are different polarization states. We can superpose them, and we can perform interference experiments with these polarization states. So this is how one can depict them. So now we want to examine one very simple problem where I have a 2-photon decay of an atom. So I have an atom which is depicted by this cartoon, the blue blob here, and it has certain energy levels, and these energy levels are connected by these transitions with frequency omega 1 and omega 2. So when there are these transitions taking place, there is an emission of photons which go in a certain way, and this emission is constrained by the fact that the initial state is created at that there is zero angular momentum. So when this happens, there is no net change in angular momentum. For no net change in angular momentum, what will happen is that the resulting state when these 2 photons are emitted can be written in this form. It's a non-separable form. This form is, so 1 and 2 correspond to the 2 photons, these numbers, and this is a symbol for writing a state. It doesn't matter, if you don't know, just imagine that this is just a way of writing a state. So R1 and R2 means 2 right circularly polarized. It means first photon right circularly polarized, second photon right circularly polarized. So if there is no net change in angular momentum, they have to be anti-aligned. So I have R1, R2 and L1, L2. So that's the sum. This can be written in terms of horizontal and vertically polarized photons also. This is just a very elementary transformation. So if we can go to the previous slide, you will see that there is this R which can be written as H plus I times I is square root of minus 1, V, and L is H minus IV. So one can go back and forth between R and L by putting these transformations, and so one can write these states. This is a state which says jointly what is the state of 2 photons. So 2 photons as they are emitted from this atom are found in this state, which can also be written in this form. Right? So now we want to perform an experiment. And the experiment is as follows: that there is this atom and 2 photons which come out, and then I have a polarizer here and a polarizer here, this yellow thing, and this polarizer turns the plane of polarization by an angle θ1, whereas this one changes by θ2, which is pi minus θ2 with respect to this. So if I draw a line straight like this angle here, which is θ2, is actually pi minus θ2 from here. So this changes polarization by an angle θ2, this by θ1. There is a detector here, detector there for the 2 photons, and we are making a measurement here which is a coincidence measurement. That is, this one records only when D1 and D2 both report a photon. So if they are coincident, then there is a coincidence event. And we would like to count the number of coincidence events. The number of coincidence events are calculated like this, that I have the initial state which was P12, which you saw in the last slide, and we would like to see what is the probability that this state is projected onto H θ1, H θ2. That is, from this state which was created together when there was a 2-photon decay, what is the probability that it passes this polarizer like this and this polarizer like this? So you make a little calculation, and you basically, it's a very simple calculation where you write H θ in this form, and you substitute here, and you can immediately show that the number of coincidence counts is actually cosine square of difference of these angles, θ1 minus θ2. So if we say that θ1 minus θ2 is some angle, then cos square θ1 minus θ2 will start with 1, and it will go down to it will go down like that, right? θ1 equal to θ2 will be cos square 0, which is 1, and then it goes to 0. So it decays like that. So all right, that's a coincidence count. Okay. Now this is and attempt to teach you how to, and I'll come back to my talk, just this is a digression which I must make because I'm going to use a certain symbol. Here I want to just make a 2-minute remark on the connection of what is learnt in quantum mechanics in usual curriculum and how is it different from what happens here. In the usual curriculum, when we study quantum mechanics, we have some initial stages of developing history and old concepts of quantum mechanics. Then we go to a quantum system like harmonic oscillator or a hydrogen atom. So we have one system, particle in a box, on different geometries. So we work with one system and we study quantum mechanics of one system. Here we have two quantum systems. So we have to entangle the two quantum systems. A single quantum system has no necessity of entanglement. But here we have two quantum systems and they entangle. When they entangle, their joint state is written in terms of what is called a tensor product. And a tensor product is denoted by this symbol, and it's calculated like this. If I have a state written as a column vector, then is this column vector and this CD. It basically is very simple that A multiplies C, then A multiplies D. So I have this. B multiplies C and B multiplies D, so I get this. So if I have a 2 by 1 column vector times a 2 by 1 column vector, a tensor product is a 4 by 1 column vector. In general, tensor product of two states which have dimensions say n1 and n2 or components n1 and n2, the tensor product has components which are n1 times n2, so that becomes a much larger size state, right? And this is the way we work with entanglement. An entangled state is written as a tensor product of the individual states of the two quantum systems. Now we come to the first important thing, which was a work by John Bell. John Bell addressed the problem which was raised by Einstein. The problem that Einstein posed was the following. Einstein, in his special theory of relativity, had a postulate which said that no signal can be sent with a transmission speed bigger than the speed of light in vacuum. Okay, so any 2 points can be in contact with each other if they are causally connected like this. So that is a statement of locality, that this is a local theory, that you can actually communicate with the 2 points. And then there was a concept of realism, and realism is something where I talked about the moon. So that is the realism, and the local realism is the foundation on which Einstein wrote his paper. And there were certain contradictions which was brought out by David Bohm, and we're talking about one of these contradictions which were handled by Bell in 60s. It's connected to our discussion of two-photon decay. Here we have a state which is produced as a two-level system where we have two spins which are up and down, and we create a singlet like spin 0. One of the spins go away in this direction, the other spin goes away in this direction. This is a realization of Einstein's work in the hands of David Bohm. And then David Bohm says that one electron goes here, one electron goes here, and then there is an apparatus here which is called the Stern-Gerlach apparatus. This Stern-Gerlach experiment measures the spin of an electron, whether it's up or down, that kind of experiment. If we have a spin which experiences an inhomogeneous magnetic field, then it is projected up or down depending on an individual measurement at that point. So this can be up or down. This Stern-Gerlach experiment here and an experiment here. So apparatus here. So here there is a projection of spin along a direction A. This one is a projection of spin along a direction B. And the probability that one is trying to find is that this is my entangled state of two electrons that I created here. This entangled state is then projected one along this direction, one along this direction. Sigma 1 and sigma 2 are spins. So spins projected along A, you know that dot product is a projection, and sigma 2 is the spins of the second electron projected along B. And so this one calculates the probability of finding a projection of spin along A here and a spin of electron along B here. And there is an assumption of locality here which says that this measurement does not influence this measurement. So they are like independent measurements, completely independent, so they do not influence each other. And if we make this calculation quantum mechanical, then a few steps of algebra give us that this will be like minus A dot B. So this is a unit vector, this is another unit vector, and this is the result that you get by just doing this calculation, which is putting this state here and just performing calculation. You get a thing like expression minus A dot B, very simple expression. So so we go back. Yes. Now here, what is the big deal about this experiment? The point is, suppose here, after measurement, I find that the electron that comes out has a spin up. Because this was produced with zero net angular momentum, zero net spin, this one must be spin down. And this is very far, not locally communicable between these 2 points. So this measurement, cannot possibly be known to this point because it can be very far and you cannot send light. So you can have the distance which is greater than speed of light multiplied by the time taken for the signal to receive a message from here. But I automatically know, because I have zero angular momentum here, that if this is spin up, this must be spin down. The question is, at this point, when I am making an appeal to a conservation law and I am not making a measurement, is it a real observation? Is it actually real to say that this spin is actually down and I have not made a measurement here? Is it possible to make any conclusion about this spin knowing that this spin is found to be up? So that's a problem. There is a more difficult problem which I come to very shortly. So we go further, and there was a theory which was based on hidden variables, where people said that maybe if you don't want to use conservation law, there may be a certain hidden variable, and one can invent some hidden variable theory very consistently and show that maybe one can explain the concept of reality by using hidden variable theory. So let's not do this, and let's go further, because we'll try to Now, what Bell found, I have to go one slide earlier. So let's go, just a second. Let me go to, just a second. This is the going down, yeah?
Yeah.
This is going down or up?
It's going down, sir.
Yes. Okay. Let me come to this. So again, we are drawn the same experiment. We have spin 0, total spin 0. We have an electron which is going this way. We have an electron which is going this way. And so let's say that this is z-axis. Let us say that this is x-axis. So there is a spin, there is a projection which is possible. The spin, if this is spin down, this must be spin up, but that is not possible to say unless we make a measurement. So here we have an apparatus, a polarizer, after which we know that this electron has a spin down along z-axis. Then naturally we would say that this electron must have a spin which is up with respect to z-axis here. But suppose now, instead of measuring z, I measure the x component of the spin for this. So I make a z component measurement here, but I make an x component measurement here. Can I say that because I made an x component measurement, so I know the x component of spin, but because I made a z component measurement here, and I know that this is s equal to 0, so the z component must be spin up, must be up. Can I say, without making an explicit measurement of z component here, can I say that I know x and z component of spin simultaneously? Because I measure z here and I measure x here. I know z here, so I should be able to say that this must be opposite with respect to z axis, but I make a measurement of x component, so I know the x component. So I infer z component and I measure x component. Can I say that I now know x and z components of spin together? In quantum mechanics, there is something which does not allow us to measure x and z component of spin together, because they do not satisfy commutation relations. So there are certain uncertainty related relations, which do not allow certain observables to be measured together, but here I am able to make an inference about two components which are not supposed to give an outcome together. So is the inference of z component a reality or not? Is it real? So these kind of questions say that the quantum mechanical description of reality by the wave function seems to be incomplete, or when the operators corresponding to two physical quantities which do not commute, like Sx and Sz, the two quantities cannot have simultaneous reality. Is it that they are not simultaneously real, that the x and x component, z component of spin cannot be considered real simultaneously, or is the problem with the description of the state in terms of wave function? What is the problem? So we go next slide. And so this brings us to these four people: Clauser, Matthew Horn, Abner Shimoni, and Richard Holt. Unfortunately, these three are no more, and John Clauser is one of the Nobel laureates of this year. And here they proposed an inequality which I want to bring to you in next 10 minutes or so. How much time do I have? Yeah, okay. So now you have to concentrate a bit and see what is happening. So there is some Charlie, which is C, who prepares two particles, and so these two particles, when you prepare, you mean either in s equal to 0 state or entangled state. They are prepared, and one of the particles is sent to Alice, the other one is sent to Bob. So there is an entangled pair of particles. Entangled pair is like that combination you saw with xi A earlier and those kind of things. So you create an entangled state of two particles, send one particle to Alice, one to Bob. They are entangled. Even if they are far, they are entangled. Okay. A receives this particle and it can perform two measurements of observables with properties some PQ and PR. So these are names of the properties. I'll come to the exact properties and example shortly. But for the moment, just bear with me that there are certain properties, PQ, PR, and these can be +1 or -1. And to make this measurement, to decide upon which measurement to make, A chooses randomly, and randomly is exemplified as tossing a coin. Okay. Now, suppose as a result of this measurement, A's particle has the value for observable Q. Value is Q. If you measure PQ, you get value Q. That is, you measure angular momentum, you get 0. So angular momentum is like PQ, 0 is like Q. So outcome is Q. For the property PR, the outcome is R. Yeah. Then B can also measure. So B is measuring two things, which are PS and PT, and the outcomes are S and T. They are again +1 or -1. So it's very simple. There are PQ, PR. PSPT, two properties, randomly measured, values can be +1 or -1. Both these are performed at the same time, so they are causally disconnected. Because they are at the same time, you cannot communicate the answer of one to the other. So they can't disturb. Now you consider this quantity. You have Q, R, S and T, 4 measurements. You made 4 measurements. A has made measurements and got the answers Q and R. B has made measurements, got answer S and T. And with Q, R, S, T, you make this combination QS plus RS plus RT minus QT. You just do that. So this can obviously, with simple maths, you can take S common, write Q plus R and R minus Q. And if you take all possibilities of R and Q being 1 or -1, you notice that this sum, this object, can be only ±2. So here I have written everything, all cases, this can be only ±2. So Alice and Bob make 2 measurements on 2 quantities, get 2 answers each, +1, -1, you take all possibilities. This quantity can be only ±2. Okay. Now suppose C, which was Charlie, prepared particles with some noise such that before the experiments are performed, the system is in a state such that capital Q is small q, all these quantities take specific. So when we said Q, it could be +1 or -1. Now we are saying, specifying exactly that capital Q equal to small q, like +1, or capital R equal to small r -1, or 1 or -2. We are saying that. So this is a realization which will take place with a probability which is P. P is the probability that the values of Q, R, S and T turn out to be small q, small r, small s and small t. Okay. Now we want to find the mean value, or what is called the expectation value of this. Expectation value, as you know, is given by probability multiplied by this sum. The probability multiplied by this sum is the expectation value of this quantity that we are talking about. And because this sum is always less than or equal to 2, so this we can write as 2. There is a sum over probability, and probabilities can be only summed equal to 1 or less than 1. So this sum, the mean value, can be only less than or equal to 2. Right? So we have a description where we say that we perform an experiment, and this experiment has to be repeatedly performed. I'll show you an example of electron interference later on, which exemplifies the meaning of many runs of the same experiment. So we have this mean value, that is, to get a specific answer here, the expectation value is less than or equal to 2. Okay. But I can also write mean value by rewriting this sum, by taking each term outside, each term, and have expectation value of each one of them, expectation value QS, RS, RT and minus QT. So I have an inequality which says that expectation value of each of this product taken together is less than or equal to 2, and this is called the Clauser, Horn, Shimoni, Holt inequality, CHSH inequality. By repeating the measurements made by Alice and Bob, these expectation values can be calculated, and this can be verified experimentally, no problem. Okay, so we have this object, right? We have applied our common sense. In this case, we have taken A and B, and we have given them the opportunity to randomly making measurements, and actually exhausted all possibilities, and we have got this answer as an inequality. Right? Now let's go back to quantum mechanics, okay, and say that C has specifically prepared a state which is like this. This is a tensor product of 0 and 1. When I say 0 and 1 like this, it means that tensor product of column vector 1, 0 tensor product 0, 1. So one can easily do these calculations. So that's it. And this is a state which is prepared where you send first qubit to A, second qubit to B, and now you say that I want to perform, that Alice and Bob perform these measurements. That is a Z1 measurement. Z1 is a phase measurement which is in terms of polymatrices. So it's basically a matrix which is like 1, 0, 0, minus 1. A 2 by 2 matrix, 1, 0, 0, minus 1. Such a state, if it acts on the spin up, it keeps the spin up as that. If it acts on spin down, it says minus times the spin down. So it's just that. And the X is the spin flip. So if I have a spin up and X1 acts on that, it will make it down. So this is the combination of operators that are chosen. That is, Q is Z1. When I say 1 or 2, it corresponds to the first qubit or the second qubit. So this is the first state, this is the second state. So if I take Q, S, R and T as specifically these operators, these matrices, and perform the calculation for the expectation value, I get, so this expectation value is with the state in the last slide. The last slide, so earlier slide. Yeah, with respect to this psi, we have calculated the expectation value. The next slide, please. And I get for QS, RS, RT 1 over square root 2, and for QT minus 1 over square root 2. And if I put all this together, I get a 2 square root 2 for this quantum mechanical state. And with all the probabilities which we had carefully calculated, which was our common sense idea of repeating measurements by randomly taking all possibilities into account, we get less than or equal to 2. If you do an explicit quantum mechanical measurement, we get equal to 2 root 2, and they are in complete contradiction. So experiments show that this is wrong. Experiments show that this is what you get. So that's too bad, because we did the maths and we thought the math was right. And it was right, there was nothing wrong with the math. But we got an answer which was not experimentally valid. So quantum mechanics is fine, but what does it mean? What is wrong in our common sense? What did we miss in this case? Right? So we made two assumptions tacitly in our discussion. These two assumptions were that the physical properties that we were talking about, PQ, PR, PS and PT, these were for the Alice and this was for the Bob, they have definite values like this, which exist independent of observation. That is, the moon is there whether you look at it or not. We assume that. This is the idea of realism. That is assumed by Einstein. It is very much ingrained in our mind. We say that, we know that it is like that. I mean, if I don't look at this idol, I'm sure that it is still there. And here one is trying to say that you cannot make this kind of statements. That the physical properties have definite values like this which exist independent of observation. You must make observation and only then you say something. That is realism. The other point we have assumed is that Alice's measurement did not influence B's measurement, then that is the assumption of locality. That there is no signal. They were measured simultaneously, so you could not have communicated. So one of these has to be wrong. One of these has to be wrong. And locality is linked with Einstein's description of special theory of relativity, the space-time description. So either you change the space-time description, or you change your common sense way of thinking about existence of values assigned to certain objects. So either you abandon reality, or you abandon space-time description of Einstein. So both are very problematic things. Okay, so this is the idea of entanglement, and this entanglement has been, of course, experimentally verified, and it is acting as a resource. And let's not go through the proof of this, except that I would like to just tell you that there is a very elementary way of saying that if you give me a moment and switch gears, and you think about computer science for a moment. In computer science, these days we work on quantum computing and so on. In classical computer science, one of the very important things that was conquered in 1940s by a person called Richard Hamming was that he could find ways to correct errors. Our usual laptops, etc., and computation, whichever is done, whenever we do any calculations, there are errors occurring all the time. There are hundreds and thousands of errors. And on the fly of calculation, these errors are getting corrected. And that's why all the computation and errors and communication, sensing, everything works, because there is an error correction. And one of the most important ideas behind error correction is that if you have a state, you can keep a copy of that state. And then you can, if something goes wrong, then you can use another copy. In quantum mechanics, the problem is that you can't make a copy of a state. There is a theorem which says no cloning theorem. And the no cloning theorem is a very elementary proof, and you look still not completely destroyed. So I'll show you this proof in 2 minutes. What is the meaning of cloning? Cloning means that if I have a state psi, I can create by a transformation itself and a tensor product of itself. So I can have two copies. Having a copy means I have the state with a tensor product of itself. That's a copy. So I have a state, I made a copy. But if I can make a copy of a state, I should be able to make a copy of another state, which is phi. I should be able to make a copy of that state. If I can do that, I should be allowed to make a copy of a linear superposition, because the entire quantum mechanical description rests on linear superposition. Quantum mechanics is a linear theory. So if there are two states, arbitrary superpositions of these two states is also a valid state. So if I can copy this, I should be able to copy this, and I should be able to make a copy of a linear superposition, which is a tensor product of itself. But look at this. If I see how psi was copied, it went to this tensor product. So if I go from here, I get A psi tensor product A psi, and from B phi, I get B phi tensor product B phi. But you see that this is not equal to this. There are no cross terms here. There is a term here which is phi and psi, and there is no such term here. So if I can copy two states, I cannot copy linear superposition of two states. And because linear superposition is underlying interference and entire quantum mechanics, because of its linearity, does not allow cloning of a state. That is cloning of a known state, unknown state. If I don't know a state, I cannot clone. So, and quantum information, which is embedded in a quantum state, cannot be copied. And so if there is an error, too bad. You can't make a copy of that. So linearity and cloning do not go together. Okay, and but nevertheless, the other Nobel laureate, Anton Zeilinger, he showed the following thing. He showed that even if you cannot copy a state, you can actually make a teleportation. You can send a copy of this state to a distant place. So this can be teleported. And teleportation is an easy thing to show. That is, it's done like this. Teleportation basically means you transmit enough information using classical bits so that an unknown quantum state can be reconstructed at the other end. If Alice has a qubit, which she does not know, qubit is a superposition of 0 and 1 state. That's a qubit, like you have classical bits, 0 and 1. Classical bits are on or off. Quantum bits is a qubit, which is a superposition of on and off. So if Alice has a state which is a superposition like this, then using an entangled pair of two photons which are like this entangled pair, one photon is sent to Alice, one to Bob, and one can actually entangle these two states, the unknown state with the EPR pair, the Einstein-Podolsky-Rosen pair, which is an entangled pair, and you get a state like this by doing a very simple algebra. I mean, there are 2 terms here, 2 terms here, and you get 4 terms here. The first 2 can be handled by Alice, the third one is handled by Bob. You make this, prepare this state, and then you perform certain transformation. At the end of that transformation, Alice measures the first 2 qubits. And once she measures the first 2 qubits, she sends that answer. So first 2 qubits can be only 0001, 1011. And so Bob receives one of these. If he receives 01, after Alice measures the first 2 qubits, he makes a transformation X on the state which was given to him, and he can reconstruct the original state, because this is the state he receives. He makes a transformation of bit flip. This is bit flip. This X acting on this gives you 1 becomes 0 and 0 becomes 1, so it becomes A0 plus B1. So like this, by just a transmission of 2 classical bits, a state can be constructed far away by entanglement. Right? This can be used to set up quantum internet, quantum communication, which is through what is called an entangler. So if I have an entangled pair here and another entangled pair here, where 1 and 2, these photons are entangled, and there are 3 and 4, these photons are entangled. So I can have 2 and 3, so I have these 2 pairs. I can use an entangler to entangle 2 and 3 in a certain way, so that because of this entanglement and that entanglement, this 1 and 4 get entangled. And we can set up this entangler wherever we want for each photon pair and actually make a whole internet out of it, set up communication, which was realized in 1998, even experimentally. Experimentally, the last thing which has been done is a communication over 1023 kilometers of teleportation. A pair of photons, entangled pair of photons, has been communicated from Beijing in China to Vienna in Innsbruck in Vienna here, and this communication has been carried out with the help of a communication satellite set up by China, which is called Mikios, and now they are right now trying to make an experimental advance which establishes communication for over 10,000 kilometers, and that would happen. So to come to towards the end of this talk, I would like to make a perspective of what we have discussed, and before the perspective, I just want to show you. I don't know how many of you know about interference of 2 electrons. Have you read about interference of 2 electrons? I mean, there is this double slit experiment of Thomas Young, where you have done this in your school, right? The double slit experiment, you have an interference pattern in the end. This is done with light. Suppose I want to do this with electrons. So I make 2 slits and send electrons. These electrons go out because electrons are like matter waves. They will interfere and make interference pattern, and I should be able to see that. This is discussed by Feynman and many other people as a thought experiment. In 1989, by Tonomura, it was actually performed as an experiment where there was an electron beam which was sent from here, and there's a solenoid, and these are electrostatic plates, so that electrons do not go out, and electrons find 2 ways of combining here, and they form interference fringes on this zinc sulfide screen. So there is electron interference, which was shown by Tonomura in 1989. I don't know if you can see anything here, but I wanted you to see something, but I see that you can't see anything. So let's go to the next slide. Anything here? Kuch dikh raha hai? Is there something? Can you see some dots here? I mean, there is one dot, a few dots here. Not too much is visible, actually, because of too much light here. So these, so this is what you see as the electron interference builds up. You start the experiment, electron goes there, makes a dot. Each electron corresponds to a dot here. And these dots do not have any definite pattern. Actually, we need this also to be off for is it possible to switch this? We'll try. Because it gives a very important message. Nothing. Okay, doesn't matter. So we go to next slide. Yeah. So now you see something? Yeah. But you see it's already too much that you see here. Because in the previous slides, there was a random set of dots. And these random set of dots have no pattern to start with. And this interference pattern actually builds up. Now you see certain fringes. There's some linear fringes that seem to appear. And if you go to the next slide, so those are the fringes which show up, and they are seen here. Each dot here is an electron. Now, this is something to be thought about. I had an electron beam. We have two ways of going. None of that is changing. Electron beam source is also not changing. It's the same source. So when each electron is sent by the same, in the same experiment through the same path, why is it that they keep coming somewhere here, then here and there, etc., and which seems random? Eventually you find that they are not random. They are actually organized in fringes which are predictable. You can calculate and actually say that this is the fringe width depending on the experimental details. So this is the nature of quantum measurement. That is, you make repeated measurements with the same conditions, and you eventually arrive at a truth which is not statistical. Because if it was pure statistics, that was common sense, and that would give you wrong answer, like in CHSH inequality. So with this, I want to make now a few remarks, which are that historically, with our experience, whatever was possible for photons was eventually shown for matter waves. That is, there was interference with light, then there was interference with electrons, then there was atoms, and so on. Photons interfere, light interferes. This was shown in Thomas Young around 1820. Electron interference, as we saw just now, was shown by Tonomura 1989 experimentally. Fullerenes, which are C60 clusters, 60 atoms of carbon, they also interfere, and that experiment was shown by Zeilinger in 1996, one of the Nobel laureates. And this has led to eventually optics with atoms, interference with atoms, the PISA-like experiments with atoms, like free fall experiment of atoms, and these have been used to actually measure the gravitational constant and so on. And these are far-reaching consequences, like your GPS works on the value of the gravitational constant. If you know the value of G more accurately, your GPS works even better. So it's directly connected to the, so is that the next slide? Yeah. Right, no, this is the next. Right, the other thing is, this is what we said. In terms of entanglement, photons entangled, so light entangled. To create entangled pair of photons, you need what is called parametric down conversion through a crystal. You send a light through a crystal of a certain type, and you get two photons which are entangled. Experimentally, electrons are entangled. This was seen in Stern-Gerlach experiments. Atoms are entangled. Molecules are entangled. For the teleportation, we saw that photons have been teleported. In future, I would imagine that whatever is possible for photons, electrons could be teleported, states of atoms and molecules could be teleported, and this can make more and more complex paradigms of teleportation. So, the other point that we have learned through the works of Bell and Clauser and Alan Aspe is that either one must totally abandon realistic philosophy, or one must dramatically revise the concept of space-time. There is no reason that we should choose one or the other. It is probably very likely that both have to be modified. and that would be the physics of tomorrow. There are related fundamental questions connected to how would you describe quantum free fall of atoms, identical atoms in different states, how would they free fall? How is that connected to the idea of mass in quantum mechanics? And when we say mass, according to general theory of relativity, mass is connected to space-time being curved. So we have to worry about free fall and trajectories in curved space-time. But when we talk about mass and particles, we are talking about fields. And so fields in curved spaces, the free falls in curved spaces, and superposition of massive objects. Massive objects can be electrons, atoms, molecules, and then massive objects can be anything. It depends on how precisely you can make measurements. So science of tomorrow rests on asking more and more deeper questions, and so we have to keep thinking and not give up and not be biased by any preconceived notions. Challenge everything and base your ideas on fundamentals and on measurements. So with those ideas, I want to thank you for your patience.
Any questions from the audience? Faculty members? If there are no questions, may I please request Dr. Santosh Mani to please felicitate Sir for his wonderful speech. Yeah, to Sir Santosh Mani. Thank you. So this moment is a part of our outreach activity of Nareshwadi Learning Center, created and drafted by our Wali community at Dhanu. Now may I please request Dr. Jujendra Satam, Associate Head, Department of Science and Humanities, to please deliver the vote of thanks.
Hello. Thank you so much for giving me an opportunity to propose vote of thanks. I would like to thank our speaker, Dr. Sudhir Jain, for his enlightening talk. I'm sure, sir, that your talk must have enlightened and ignited research minds of many of the students and faculty members. Special thanks to Vice Chancellor, sir, Professor V.N. Rajasekharan Pillai, for suggesting us such an event to ignite young and enthusiastic research minds. Also, special thanks to Provost Sir, Dr. Raghunath Shevgaonkar, Dr. Parvati, and CIRAC team for making this event successful and for all the coordination. I would also like to thank I would also like to thank students from various disciplines. Shri Ashok Kundar,